of you to this webinar as well. Today I give you an introduction into the scripting with Python for the UDE, our Universal Debug Engine, in order to automate debugging or to do automated tests. So next slide. That's the agenda for the next 45 minutes. I will start with a little theory and try to keep that short, of course. Then we move on the practical side. That is the more interesting part. In this practical part, I will go through a simple example of a Python script that should run a single automated test and remotely control the debugger. I will go step by step through it so you can see what we are doing. Once we understand how the scripting is working with UDE, I will extend at the end the script so that we end up with a complete tester that also calculates code coverage in parallel to prove the completeness of our test. Okay, then let's get started. So what is scripting? You expect scripting from every tool that you are using. And in UDE, we have also support for scripting. We call this UDE automation feature. The UDE automation is included in every debugger base license, so there's no additional costs for using it. The purpose of UDE automation, as the name applies, is basically to automate debugging and to automate testing by controlling the debugger from other software. This can be done using a script, so that's the topic for today, but you can also control the UDE debug tool also from third-party software, such as commercial test tools. The heart of the UDE automation is the UDE object model. This is an open and flexible software API that provides access to all the debugger functions. So in this object model is based on the component object model from Microsoft that is deeply integrated into the Windows operating system, and it can be used with many scripting and programming languages, and that's very practical for us because we don't need to develop a proprietary scripting language for UDE, nor we are bound to a specific scripting language. That means you can use any scripting language you like. You can work with your existing knowledge and of course your preferred tools, and you don't have to learn new things. So coming to the object model of UDE, that image illustrates only a part of the UDE object model. As you can see, it is a hierarchical structure of objects that are linked together. Each of these objects provide interfaces that give you access to almost all the debugger functions. Because of the hierarchical structure of the object model, all of your scripts must first access to a top level, or we call it also root object. And from here, you can access the next lower objects in the hierarchy using access functions or object properties. So to get to a specific object that provides the debugger functionality you must query all the objects in the path through the requested object step by step. And at the very top, there are two objects that are used for starting with obtaining all the objects, and that is first the UDE launcher. This object is used if you want to create a new UDE debugger instance. So basically, if you want to start UDE, And there's another one, which is the UDE running instance manager, which is the object used for connecting your script to an already running UDE. And from these two objects, you get the UDE application object, and this is where you can start obtaining all the objects of the debug tool that you need for your automated debug script or test script. And this is the actual root object of the object model in UDE. And from there, you can access all subsequent objects that provides you the necessary debugger functions. So all the objects in the hierarchy provide get methods or object properties that you can use to obtain the next lower object in the hierarchy. And this is how it works. This is the essence of a script. You see the 4 lines needed to start an application on your on one of the cores of a multi-core system, for example. You start with the running instance manager in the first line, access the workspace, which is the debug session, or which has all the knowledge about the debug session. The debugger itself is responsible for controlling one of the cores in your device under test. And of course, you can use this to start the application running on that specific core. So each of these objects implements methods and functions, or functions. So there are 2 terms of them, and provides also properties. We have a documentation of them. So you see a screenshot of our documentation system of the UDE help system. On the left side, we have all the functions described that the debugger interface provides, and on the right side, we have the properties of the debugger interface. So the screenshots, as I said, are taken from our help system, and you see here all the blue text can be clicked, and you get more detailed information on how the definitions of the functions and properties look like. This is given in a generic form here on top, but you get also a description text and also an explanation of the parameters. And finally, we have some code examples, for example, for Python and also for other languages that we support. Okay, with that, we have enough talked about the theory, and it's time to look at the whole thing in practice. In the next few minutes, I will create a Python script step by step that will do a basic test for a simple application. The application to be tested runs on an Infineon tri-core Aurix device, TC39, and the application implements a simple clock. So we increment minutes, seconds, and hours step by step. And what we want to test in the first step is the wrap around when a minute is up. So we expect that the seconds are reset to 0 and the minutes are incremented by 1. So that's the hardware setup on my desk. I use an UAD2 Pro to connect via the DAP interface. That's the UAD2 Pro here. This is a part of our Universal Access Device family. And we connect using the DAP interface to the tri-board with the Aurix. The debug probe is connected via USB to my PC where the UDE is running. For the script development, I use the Anaconda Python distribution, and for writing the script, Visual Studio Code. If it's not installed already in the Python distribution, you will need to install the Pywin32 library, which provides you the necessary functions for using COM. And for the writing the scripts in Visual Studio Code, you will need to install some extensions that are Python and PLS. And then you need to set up the Python interpreter because the Visual Studio Code itself does not contain an interpreter. But will not be shown yet in the demo, so it's just for your information if you want to use the Visual Studio Code. For the demo, I use an additional extension in Visual Studio Code, which is so-called the Jupyter Notebook. That extension allows you to write Python scripts step by step and execute each step separately and see how it works. It's a kind of basic debug technology or debug method. Okay, then let's go to the UDE. I had already opened the UDE and I load a workspace, which is already prepared, which contains the application. I load the application into the device, and I can show you what the application is doing. We have some functions here which are executed periodically and counts up tens of seconds. And then once a second is up, then we use the update seconds function to increment the seconds or check if a minute is up. And then we go to if the minute is up, we go to update minutes, counting the minutes, and so on and so on. And we want to test what happens if a minute is up. So we want to check the update seconds function with a small script written in Python. For that, I use the Python, the Visual Studio Code, and first of all, we have to create a new Python file. I use the Jupyter Notebook here, and that is the clue. Here we have cells where we can type in Python commands and we can execute each cell separately, so we can execute our Python script step by step. If you are finished with your script, you can save it, of course, as a Python script and then execute it from the command shell, for example. Okay, so let's get started with writing the script. The first thing we need is to import some libraries, and the most important one is we need the Win32com library, which allows us to communicate with the Windows with the common object model. So I execute that. You can't see here anything. It is in the background, the libraries are loaded. And once we have loaded this library, we can get access to our UDE. And the first thing is that we need access to the running instance manager of the UDE object model, because this is registered in the Windows registry. We can use the wincom client dispatch function and get access to the running instance manager or create a new running instance manager object. You can use the name, of course, to get this. And once we have executed, then we have the running instance manager object available and can use it. If not, so these lines here are for checking if we have a running instance of UDE already opened. There is one opened, so we get no error here. The next thing we want to do is we want to ask the running instance manager for the UDE which is running. So we ask for the first instance, so with the index 0. And that you can see everything. I print out the UDE version. So we have UDE version 2025.2 already running. And now we can have access to the UDE application object, which we named UDE. So from that, we want to start our application. To start the application, we need two things, step by step. First is we need to get the workspace, that is the debug session here. The workspace can be obtained from the UDE application object. The line, what is really needed is that one. That one prints out the workspace file location, and then we check also if we have already a successfully connected target, so the device. So we get a successful connection. So everything is connected to the device under test, and then we can start our application. For that, we need to access the so-called core debugger. We have several cores here. You see we have, it's in some we have 4 cores connected, but we only need 2 cores to control. The core 0, which is that one which starts the application, and the core 1 is that one which executes the clock. So we ask the workspace for the core debuggers for core 0 and core 1. So we have a get function here for the core debuggers. You can use the name, or you can use also the core index, but the name is more convenient, I think. So once we have the core debuggers available, we can start the application by using the go command. If we execute this, then we see that our application is now running. We see the values of our clock are incrementing. So these tens of seconds, these seconds, and once the minute is up, we expect that the minutes are also incremented. Okay, we want to check or want to test the update seconds functions, and for that, specifically the wrap around when a minute is up. So we have to provide a test case for that, and the test case would be that seconds is 59. The result should then, after executing that the seconds are reset to 0. And we provide also a test value for the minutes. For example, we are using 10 that we can check later on that we get after executing this function as a result 11 for the minutes. It is always a good idea to write in the test cases not during runtime. So breaking the application before is a good idea. For that, we are using breakpoints, of course, and breakpoints are core specific. So the breakpoints are part of the debugger object. So we ask the debugger object of core 1 for the breakpoints object, and then we use the breakpoints function add and get result to set the breakpoint on the function update seconds. If we execute that, then you see we set the breakpoint, and instantly we also hit this breakpoint. To make sure that we hit the breakpoint, I have added also these line here, or these check here, that we are make sure that the application is stopped at the breakpoint. So now we can write in the test cases. So the debugger object provides functions for writing values, for example, writing variables, or writing into memory, or writing into registers. We are using the write variable function to write our test vector. So seconds 59, I said this before, and minutes to 10. And then if we do this, then we see the new values also in our watch window. We can also read out these values. For example, we need for our test a variable with the current value of the minutes that we are using later for comparing the results against this minutes before variable. But I can, of course, do this within the script, but in this case, I want to read out the values also from the target. So, okay, we read the same values as we see in the watch window. Everything is okay. And then we can remove that breakpoint and prepare the application to proceed to the end of update seconds. So we want to execute this and stop at the very end of this function. And for that, we remove the breakpoint at this location, and we want to set the breakpoint at the last line here, which is line 8. So this is one of the possibilities to set a breakpoint. For example, you type in or use the name of the function and an offset of lines in that function. You can also set a breakpoint using the address, and there are several other methods all described in our documentation. If I execute this, you see we have removed the breakpoint, and a new breakpoint is now at the end of the function. And then we want to proceed with our code execution. We start the application again, wait for that the application halted at the next breakpoint, and then we can read our test results and compare the test results against the expected values. So we already know how we read a variable, and then we have the comparison. And if we execute this, then we see we have the seconds are reset and the minutes are incremented by 1, and the test has been passed. Very nice. At the very end of our very, very small script, we clean everything, remove the breakpoint, start the application again. And as a very important point, when you write scripts with UDE, at the very end, if you want to finish the script, you have to clean up everything that you, every object that you are used in the script. So by setting all the object that we are using to none. The reason for that is if you do not clean up, then the garbage collector of Python will not clean up the memory for these objects. And if you close the UDE, there will be some occupied memories there. Okay, then let's execute that. And now we are finished with our first script. We connected to the our script to the UDE, which is already running. Sometimes you want to open a new UDE, and for that you can use the script as we did before, but you have to change this script a little bit. Firstly, of course, the running instance manager wouldn't work anymore for this use case. You have to use the UDE launcher as the starting point. The UDE launcher has a lot of options to start UDE. One of them is start UDE and create a new workspace file. So you provide the workspace file name, and then you also provide a target configuration file, which has to be in place on your computer. The target configuration file describes which device you want to connect using which debug interface and probably which debug probe, which UAD you want to use. And the true at the end in the parameter list is says that you want to create a new workspace in any case, whether the workspace file exists or not. Okay, then the next is that you have to load a ELF file, of course. So some application has to be loaded into the device, because if you create a new workspace, then UDE has no idea if what's already flashed on the device, and so it is necessary to create to load and program a new ELF file here. The rest looks the same, so I skipped the lines in between. At the very end, we have to change our cleanup a little bit, of course, because now we have the launcher. You can use the launcher to stop the instance, so you close UDE and also clean up the launcher object as well. Okay, because of the limited time in this webinar, I will not show you this in a practical example. Instead, I'd like to expand the functionality of the script that we already written and turn it into a complete tester, including several test cases and also including a code coverage that should prove the completeness of the selected test cases. So in order to test the complete clock function, we will, of course, need a few more test cases. I have written down test cases that I believe are necessary for the complete test. So we have the input value here written in black, and the expected good values for the variables in green. And in parallel to the test, we want to do a code coverage measurement that should give you an indication of whether the selected test cases are sufficient to fully test the clock algorithm. UDE provides a code coverage function. And this code coverage feature is based on tracing. So that means you need a trace device or trace capable device. So I have one here. The RX allows us to collect trace information, program trace information, to be more specific. And for our test script, that means also that not only the tester has to be implemented, but we have to also to configure and execute the trace in parallel to our test executions. So switching back to UDE and switching also back to our script. So I don't reuse this script. I have prepared a script as a starting point to be more quick here. You see the first two cells are doing quite the same that we did before. So we connect to UDE. we get access to the workspace. We get access to the core debuggers, to the breakpoints, and we start the application. So application is already running. So there is there's nothing changed. And then we want to stop our application or want not to use the update seconds function as a starting point of our test. We want to test from executing the update tenth of seconds function, which is called every tenth of a second. That's why I changed the breakpointing a little bit. So okay, here we are. This was nonsense. Core1 update clock is the function that we are used as a starting point for the test. Sorry for that. Okay, and then we want to look at the code coverage in parallel. So I open the code coverage window as well. And I rearrange my windows a little bit here. Okay, that's the code coverage window. And now we can we want to write our test script or tester script. The first thing we want to do is preparing the code coverage measurement. For that, I told you before, we are using trace. So I have to configure the trace system. So the workspace contains also information about the existing trace. We call it trace streams. So a trace stream means a trace system on chip. And we want to use the MCDS trace stream of the RX device. Once we got the trace stream object here, we can use this trace stream object to configure the trace. I have a configuration prepared for that, so I can load this and configure the trace system. I show you that. I go to the tools menu and open the trace configuration tool in UDE, which is basically a graphical configuration tool where you can compose your trace task. And I have already one trace task saved on my computer, and I load this basically, and you see it does not very much. We start the trace here. We use only a small amount of trace memory. We look at core1 for the trace, and we end the trace if we leave the core1 update clock function. That's basically the configuration for the trace. And then we want to configure also the code coverage before we start our test. The code coverage is also a feature that is part of the trace functionality of UDE. It is called a use case, and we want to load the code coverage object for core1. And then this clear is not necessary at this moment, but later on it would be very good to have it. And then we set up the trace system or the code coverage for our use case. Accumulate means that we want to accumulate the code coverage results over several trace runs so that we have at the end a code coverage for all the test cases. And we want to calculate the code coverage after each trace run automatically. So we set manual control to false. Okay, we execute this code. So now the code coverage is configured. And then finally, we can start with our test cases. So we have 5 test cases. If you remember the table, then we have, can you show this? We have 5 test cases for several corner cases of our clock application. and I want to define our test cases in our Python script. So I have a kind of vectors here and structures, and these are the 5 test cases that we want to test our application. So we have the initial test vector and also the good results that are used for the later comparison. And then we can type in or can write the test vectors or test cases to the device. I select the first test case, which tests the increments of the seconds. Write the values. You see it. I have to execute this, of course. Then we write the values. You see the values has been written to the device. And then I can start my first test run. So I start the trace, wait until the trace system is configured on the device. Then I start my application. Then we wait for the breakpoint, write the test case into the device. These are the 4 lines of that. And not the test cases are already written. We read the test cases or the test results, and then we compare against the good values. When we execute that, we see we have one execution of our update clock function here. We read the values and we have a good comparison. So the test has been passed. This was for one test vector. So now we want to, of course, we want to change the script a little bit so that we do a test for all the test cases we defined. That's why we are looping through all the test cases using this for loop. This is our test vector, and we loop through all the tests. We, of course, write each test case to the device. We then start the trace, start the application, then we wait until the measurement of the code coverage is finished here with these lines. We wait for the next break of the application, read our results, and compare them against the good vectors. Okay, and once we are finished, we print finished. Okay, then let's start this application here. We see that our tests are executed and we get results, and at the same time we get also the code coverage results step by step. So from the yellow incomplete code coverage, we have now for all the tested functions a complete code coverage, and I think that makes us happy here for the moment. If you look at the other webinars from Hitex, you will see that sometimes this is not enough for your test cases, but it's not the topic for the webinar today. I'd like to show you in this webinar how it works with Python. Okay, and then finally we can make a report out of this, also using our scripts for the code coverage results. There is also a data object provided by the code coverage which allows us to create a report of our achieved code coverage. So the report itself should be output in HTML. We provide a file path, of course, a name for the report file, and some additional stuff what we want to see in the report, for example, source code lines. And once I execute this, we can create this report also from the script, and you see everything you need for documentation is part of this HTML file. At the very end, cleanup is mandatory, so don't forget it. So we remove all the breakpoints, start the application again. This is optional, that is not necessary, but what is not optional is clean up every object that you are used during your test execution. And with that cleanup, I clean up also the webinar. And I'd like to say thank you to all of you for your attention. If you have any questions, then use the webinar panel or write an email. And there will be another webinar end of October 23, about debugging and timing analysis of AutoSAR. And I'd like to invite you to this webinar. And at the end, thank you very much for your attention. Take care. Bye-bye.